Yes. Okay, so now we're going to talk about the first transport coefficient, thermal conductivity. So let's dive into what is transport. Okay, it's, again, we're in non-equilibrium systems, so whenever there's an inhomogeneity, the system wants to respond. It wants to come to thermal equilibrium. It wants to come to equilibrium in mass, equilibrium in flow, all these different things. So this inhomogeneity is gradients. And so, like I said, the simplest gradient you can think of is a pile of sand. Okay, because from our earliest days, playing in the sand, right? You make a little pile and it rolls back downhill. So the pile is the gradient and the rolling back downhill is the flux. So we have flux coefficients. Okay, now we have different transport properties. We could have matter being unequally distributed in a particular space. So like if I light a candle up here, like one of my favorite creme brulee candles, and you get this beautiful smell, it's up here, it's really concentrated, and far away it's not. And so that's a gradient. And so the gradient is the uphill part. So coming towards the candle, you have the gradient. The flux is always in the opposite direction, and it would be diffusion. So that smell would diffuse through the room. Since there's a gradient in mass or matter, then there's going to be a flux in matter as well. What about energy? Thermal conductivity. We're going to talk about that one first because it's very easy to understand too. Heat flowing from hot to cold. Okay. Linear momentum is probably the most difficult to understand. That there's a gradient not just in matter, which you can get your mind around, but it can be a gradient in anything, including speed. Like flow through a pipe, the flow in the middle of the pipe is faster than the walls. Or go to a riverbank and look at it. The flow in the middle of the river is faster than the flow at the shore. If it was the same at the shore, you'd have enormous erosion. So the shore is not moving, and so the water right at the shore is really not moving. You go a little further out, it's moving faster, faster, faster. In the very center, it's moving very fast. And that is a gradient, but it's a gradient in velocity. Okay, and so there's going to be a transport coefficient that slows it down, that opposes that gradient in velocity. Just like you pile sand into the middle of the pile and it wants to flow back down, if you pile up velocity in the middle of the stream, it wants to slow down. So the piling up of velocity in the middle of the stream is opposed by the flux, the drag that the shore produces. So since the shore is not moving, the water's moving really fast in the middle, there's a drag on that if the solution is viscous. If the solution is not viscous, there's very little drag. So this viscosity is the amount of drag you have on velocity. Okay. And then charge, you have ionic conductivity and resistance of the fluids. And so this is a picture of a mass gradient. So we have more particles on the left side of the box than we have on the right. And so if you were to plot the particles in this volume, you'd have very, very few particles, and then, you're plotting it up. There's more and more particles here. And so this is my pile, right? And so the gradient goes this direction. And then the flow, this is the flux, goes in the opposite direction. So the particles are going to the right because they're crammed onto the left, just like your sand pile. And so you take this gradient, which is the gradient is the derivative. So whenever we're taking the slope of something, we're taking the derivative. And so the gradient in 3 dimensions would be a 3-dimensional gradient. Okay. So you could have, in 3 dimensions, you could have a place where there's lots of gas, like if I had my candle sort of on a stand, and it's diffusing in all 3 dimensions. Because you have a gradient in all 3 dimensions. Okay. And this flux parameter, again, is in the opposite direction, opposite of the gradient. And this is the transport coefficient. And so depending upon what the gradient is, we have different names for the transport coefficients. And so that's where we had this previous slide here. These are the different names for the transport coefficients. So all of these things are generically called alpha. Right? in this particular case, we're talking about matter. So we have a number density. That's what's shown down here with this N with the tilde on top. There's many different ways to write that. It's the number of moles times Avogadro's number over the volume. Or if you wanted to use molar volume, which is liters per mole, and you have Avogadro's number per mole, that's particles per mole. And this is liters per mole, and the per moles cancel. And so number density is essentially inverse volume. And once again, we lose the things. Like Avogadro's number is just per mole. You know it's particles on top, but we never write out particles because it could be anything. It could be molecules, particles, stars, whatever, you know. And so we just leave the top ambiguous. But I think that's always been a problem with science. You know, this in frequency, cycles per second or collisions per second, we lose what's on the numerator because it's ambiguous. So I've never liked that. So I don't know who to complain to. I mean, science, right? But whenever you have these frequencies, or in this case, a number density, it's a number density. So you lose what's in the numerator, and it looks just like inverse volume. So it's a strange parameter. And so here's the energy gradient. So you see a container, and we're looking at temperature or energy, and the gradient goes, you know, from cold to hot. There's your sand pile. And so then we always have, and this tells you, sort of defines, or helps you in your mind understand, energy flows from hot to cold. And we kind of knew that. We know about expanding gases and so on, but this is a non-equilibrium system. So it's the energy. Cold is a lack. Cold is a lack of energy. And so this is the three ways to transport energy. We can do it collisionally, with particles randomly colliding with their nearest neighbors. And so this hot atoms and molecules have a high velocity, so they start colliding with colder ones, and they transport their energy to those colder ones. Then we have two other ways. We have convective transport, which is non-random flow of currents. So that the big difference between collisional and convective is this randomness and the flow. So convective is currents of gas, and we can set those up on purpose, like with a fan. So we can have a heating element, and we blow hot gas past that heating element and into the thing we're trying to heat up. And because that fan is blowing it in a particular direction, that's not random. Okay, so we're forcing the heat to go a particular direction. And that's our air fryers and GC ovens. So you hear on the gas chromatograph, the oven inside, it's a convection oven. So yeah, I'd love to try an air fryer, but I don't want to take up the counter space, you know. Jennifer's told me we can't take up the counter space. And so, because I heard they really reheat French fries. I mean, who hates French fries reheated in the microwave? You know, you really need an air fryer for that. But I want to try it, but I don't want to buy one, right, because of the counter space. It's not much. No. It's a lot. Oh, it is a lot better. Okay. But we have an old GC oven up here, which is exactly the same thing, you know. And so I thought about maybe bringing my fries up here, programming it in, you know. But there's a lot of stuff that's been heated in that oven, so I'm a little worried about it. That's right, nothing at all. Not the solder that I heated up in there to solder my circuit boards and the lead and the tin. Yeah. Anyway, and then radiative heat, emission of radiation from hot molecules to cold molecules is radiative heat, and this is an example that you experience. The next time you're at a campfire, and the flames are gone, and it's just the coals, and you can really feel the heat coming off of that. Block your face with your hands, and you'll feel your face get immediately cool. And the reason that happens is you're blocking the radiation. So that infrared light coming off of those hot coals is intense. And all the little temperature sensors in your face are pretty, finely tuned, right? And if you just block that radiation, you'll feel the difference in your face. And that's radiative heat. So we're just neglecting convective heat and radiative heat in these calculations for transport. So this thermal conductivity that we're talking about is just the collisional piece. So we're assuming the last two are small for our problems. Now, at a campfire, you can experience convective heat too, but I wouldn't advise it because there's a non-random current of hot gases going up, okay? If it's not very windy, all those gases are going straight up, and if you put your hand above the fire, you'll feel the convective heat, so those hot molecules hitting your hand. So that's convection. Then you feel the radiation, you can block it with your hand, that's radiative heat. And then collisional heat would be if this, we're in a still room, no currents, okay, and then the molecules are just transporting that heat from the hot coals elsewhere. Okay. So that thermal conductivity depends upon the velocity of the particles and the mean free path. So here we have our flux coefficient and that gradient in temperature versus distance. We have the heat capacity there, the average velocity, the number density, the mean free path, Avogadro's number. We can substitute 3/2 R for our heat capacity, so we're just dealing with a monatomic gas. Actually, no, let's just say we're just dealing with translational motion. So we're not talking about rotations, and since this is collisional, it's translational. And then that number density, we can put in Avogadro's number per the molar volume, and that Avogadro's number is going to cancel with this Avogadro's number, so that's a good thing. And then the molar volume, we could use the ideal gas law, which is going to be RT over the pressure of that particular substance. Okay. And so then we end up with this very simple equation of that pressure of the gas, the average velocity, the mean free path over the temperature. So what's the thermal conductivity for argon at 300 Kelvin and 1 atmosphere? Put those in. Again, we're going to use that pressure in terms of pascals. Now I've written it a little different way. I've got it in terms of joules per cubic meter. That's the same as Newton per square meter. I've got from the previous calculation that we did with argon, we have the average velocity here. So it was calculated in the earlier notes. We calculated the mean free path for argon, and then we've got the temperature here. So it's 0.0054 watts per Kelvin per meter. Okay. And so it's not a lot because we're dealing with a gas. Okay. Now we can look at these same kind of thermal transport coefficients for other substances. And let me just jump ahead to that. We'll come back and talk about the home insulation and so on. But we calculated 0.0054 for argon. For air, we've got this one. So this is the experimental value for air. So again, it's close to the same order of magnitude. Look here for vacuum. You don't have any collisions in vacuum because there are no molecules. So perfect vacuum is the best insulator. Now, sometimes we want things to conduct heat. And so our metals like copper and aluminum, so we have our heat sinks on our computer chips to sink away the heat. Okay, they're made out of aluminum. So here, the ideal gas was 0.0054 for argon, 0.025 for air. So air cool would take away that much heat. Aluminum would take away 237. Copper would be even better. So 400. So a copper heat sink would be better. If you see water-cooled CPUs, you see a little copper heat sink and the copper tubing taking the water away. Where's water? Is it on here? Yeah, water down here, 0.69. Not great. But water has a huge heat capacity, and if you have flowing water, you're connecting it to a large volume of water. So it's going to take a long time to heat that water up. And so look at diamond. That's the best one that I know of, and I think that's the biggest on the list. And so when we coat our tooling with diamond, and they have saw blades that are coated in diamond, drill bits that are coated in diamond, what they're really doing is they're spreading the heat of the cutting action over a larger part of the tool. And so, yeah, diamond is hard, that's good, but also it's for heat transfer. It's protecting the sharpness of that bit. As it's cutting, the tip is generating an enormous amount of heat in a small space and can actually melt the tip, and that makes it dull. So if we have diamond coating along the edges of that tip, it transfers the heat much faster than the metal can, and it spreads that heat over a larger part of the tool and keeps it sharp a lot longer. Okay. So that's a little bit about thermal transport. We're running past time. We'll pick up with the housing insulation next time. So applications of thermal transport.